Hey everyone, it's Jennifer. Happy Friday. I'm coming to you with an Ejectors Part 2, where I'm going to go into a little bit more detail on this topic after further research on it. I've made an attempt here to try to correct some of the issues with my illustration and give a little bit more examples of use cases and brands and all that good stuff. So the point came up of, you were just using your hand to illustrate this last time around. Can we use something more interesting, like maybe a laser pointer? Well, how's that working out for you for a laser pointer? What do you think? That work for a laser pointer? All right, cool. So let's get going with this. Ejectors Part 2. Okay, so I've fine-tuned my illustration here. It's still hard to really depict this and all the information around it with just a hand drawing, but I'm gonna give it my best shot because I'm trying to figure this out as we go along. Okay, so what we're trying to do is we're trying to move gas or steam or liquid, some other substance. We're trying to move that through a pressure and velocity change situation in order to discharge that, whatever that substance is, let's say it's gas, into wherever it's going. Okay, so just to start with, so ejectors bear some similarity to vacuum pumps and compressors. The main difference is that vacuum pumps and compressors have moving parts, and an ejector has no moving parts. It's stationary. So when you're looking at advantages of an ejector, we're looking at the fact that it's lightweight, it's portable. There's no need for a power connection. It's intrinsically safe, and we'll talk about that in the use cases. It's low cost and it's maintenance free. Who wouldn't want that? So pretty cool thing here. So now when I am talking about like a velocity to pressure change situation to move, let's say it's gas, through this ejector, we're referencing something called Bernoulli's principle, and I hope I'm pronouncing that correctly. But basically, what Bernoulli's principle states is that when a velocity speeds up, then pressure decreases and vice versa. So there's a correlation between these two. And that's the principle that ejectors work on. So now a brand name example, I kind of had to dig for this, but Gardner Denver Nash is a brand that can be looked into for an ejector. If we come over to a silencer, floating MP, in this case, MP is what they use on the discharge side for a silencer. We'll talk about that, but those are kind of like a couple of brand name examples just to get a little bit more real world with it. So, okay, so what we're doing here is we're taking steam from a couple different sources here for a reason. So we're going to start with a process vessel that in this process, there's liquid here. It's temperature's rising, so gas, it's got a phase change. Gas is coming up here. Okay, so it's coming into this mixing chamber, and we really need to accelerate that so that we can get a discharge of this original process gas that's 10 to 15 times on average more pressure versus the suction where it initially came in. That's the whole idea here. So we want an efficient ejection going on. So we're going to start with our motive steam pressure energy. Okay. It could be a refrigerant, it could be something else, but the idea is, in this case, if we're talking about a steam ejector, and there's different types of ejectors, there's a water ejector, There's air ejectors. Let's say we're talking about steam. Okay, pressure energy, we're gonna start here. We're gonna come down into this motive chest. This is what this is called. And that leads to a motive fluid nozzle where this accelerant is going to speed up the velocity for the incoming inlet gas. Okay, so it speeds up the velocity. It does that by funneling into this venturi pipe or tube here, and it's coming through, and then it's getting into this mixing chamber where it's mixing and entraining. It's a steam jet vacuum ejector. And as this is happening, that's creating audio. It's creating a shock wave of audio vibration. So 90 to 110 decibel audio. And so that vibration frequency, we're gonna look at reducing that to get a smooth discharge on our way out of this system, and we'll talk about that. So what I couldn't capture, that I had to really kind of look into a little bit more, was this idea of double choking. There's two throats here. All that really means is you've got like two venturi situations. So it's actually like funneling down a couple of times through this process. So first, right in the, first downstream area, and then coming upstream further as we get toward the diffuser throat. And I looked into that, like, okay, what is that diffuser throat? It's like an orifice, and an orifice is just kind of like, it could be you can think of it as like a deflection point, where now we're heading into conversion to pressure energy. Okay, all of this area here is part of the diffusion. These are a couple stages of diffusion here. Okay, so this is the last stage of that. Okay, so anyhow, it's a little bit clearer than it was last time I was trying to go into this. So we start with the supersonic velocity. So it's past the sound barrier. It's fast. That's why. Okay, gets into this mixing chamber. Now once it's done this mixing and entraining, it's actually in that conversion, it's being converted over to subsonic fluid flow. That's where we're getting the shock waves and we're getting the high frequency. So that's going to be addressed at the end. But let's see. So where would we find this kind of ejector? Okay, so we can find these vessels in, for example, confined spaces, pits, explosive atmospheres, mines, petrochemicals, collieries. I don't know if that's how it's pronounced, but you can find it in that those kind of situations. Also, the conversion to velocity is by adiabatic expansion. So I thought it was adiabatic. No, it's adiabatic expansion. Thank you, YouTube. Okay, so once we've got our gas, it's gone through, it's speeded up, it's 10 to 15 times pressure. Now once it's been ejected, we're going to put it through this silencer to get it to the right attenuation and the right pressure drop, delta P situation. So where is that ejector heading into? Okay, so I've read that boilers are one use case for it. I know there are others, and I don't know what those are yet. That's what I'm trying to figure out as a next step, because if it's in all these other places, ejectors clearly have other use cases than that, especially if you've got air and water ejectors. So I know this is still you know, maybe not quite as smooth of a presentation as I would hope just yet, but it's a little more information on this topic. So if you're watching this, thank you, and I appreciate it. And I hope you have a great rest of your week and weekend ahead. May the force be with you.